Hello and welcome back to Statistical Data Analysis 2. In the lecture of today, we're going to talk about random effects. As you might remember, random effects are an assumption of mixed models, and they are needed when we try to model repeated measures data. For example, data from a psycholinguistic experiment where one participant has seen multiple items, and likewise, a particular item has been seen by multiple participants. And we're going to have a quick recap of what mixed models are and where these so-called random effects appear in them, to sort of deepen our understanding. And then we're also going to talk about how to select the appropriate random effect structure in a mixed model and what the implications are. Let's take a step back for a moment and think of standard linear regression. That is linear regression without any random effects. A mathematical expression of it you can find here. So for standard linear regression and the simple case with just one predictor, the outcome variable y, the observed outcome, could be described as some intercept, beta 0, plus beta 1, some slope, multiplied with our predictor variable x1, it's the only one in this case, plus the residual error epsilon. Now, this kind of model, this simple standard linear model, is appropriate when all observations of our outcome variable y are independent, or to be more precise, independently and identically distributed from one another. That is, that there are no subgroups within the outcome values, the outcome data points, that sort of share a particular property which makes them distinct from other data points. For example, if we had our overall set of data points here, and then there was a subset of data points that belongs to a particular participant, or a subset of data points that belongs to a particular item, in that case we would violate the assumption that the data are independent, and we couldn't use such a model. Or we could, but we would violate the assumption of the model, which is dangerous for drawing statistical conclusions. But if we have a simple kind of data set where we have just one data point per participant, in that case we can use this simple standard linear model. But when it is in fact the case that we have data like this, where we have our data points, but then again there's also this subgrouping of, let's say, these three data points pertaining to participant 1, and these three to participant 2, and these three to participant 3, and so on. Well, if that's the case, then we should use a mixed model, and a mixed model will be a model that includes random effects. And in this case, because this is about subgroups by participant, we would have to include participant as a random factor. And the idea here is that you have these subgroups, so this could be the three observations for participant 1, and these are the three observations for participant 2, and so on. And it is also a crucial assumption for the linear mixed model with the random effects that these subgroups are sort of interchangeable, like they themselves, the participants, come from some independent and identical distribution of people, okay? So by including the by participant random factor in a linear mixed model, you're basically telling the model that we want to generalize our findings to the population of participants, for example, the population of English native speakers, from which we have drawn, supposedly at least, a random sample or an approximately random sample. And the same logic as for participant as a random factor also applies with regard to items. So when we have an experiment and we have like different sentences which all share the same structure or the same interesting phenomenon that we want to test, in that case we also have different items, and usually in the classical psycholinguistic experiments where we have a Latin square design, each item would also be seen by multiple participants. So another way to view these data would be that, okay, we have let's say 3 items. Usually you would have more than 3, but just for the sake of this simple illustration, you could say, okay, this data point is from item 1, this from item 2, this from item 3, and you would do that for all of them here. So 1, 2, 3. And then you could say, oh, okay, so on one view we have these subgroups by participant, but on another view, which is sort of equally important, we also have subgroups by item, in the sense that we have multiple observations for item 1 or for item 3, and in different participants. Okay, so now there is a subgroup of this, and that data point, which are all data points for item 1, or we have all the data points for item 2, and these we should also take into account, because there might be some variability that's just explained by between item differences, and by including the by item random factor in a linear mixed model, we're basically telling the model that we want to also be able to generalize our results to the population of items that we sampled from. Okay, so we constructed some, let's say maybe 3 or 10 or 20 different sentences with garden paths. But what we are trying to statistically model is, of course, the effect of garden pathing in any sentence with the same structure. But we can't obviously test infinitely many sentences, as there are infinitely many sentences supposedly that exemplify a particular structure. So we're just sampling, constructing 20 items that have this structure, and we want to generalize to the overall population of items. Just the same way that we also want to generalize to the population of participants by including the by participant random factor. So these kind of dependencies between different data points that share a particular property, like being from the same participant or being from the same item, can be accounted for using these so-called random factors, also called random effects. And what these basically are, well, they are adjustments, estimated adjustments to the overall intercept, or potentially also overall slope of a predictor, which vary randomly, but in a normally distributed way, by the category in question, so by participant or by item. And to terminologically distinguish those random effects, those random adjustments, from the overall estimated intercept or slope, we call the overall estimated intercept or slope fixed effects. Okay, so we have the fixed effects, which is like the overall trend that gets an estimate like beta 0 hat and beta 1 hat. And then we have the random effects, which are this random variability by a specific category, like by participant or by item, which is also estimated in addition to that in case of a linear mixed effects model. So as I just mentioned in passing, there are two kinds of random effects: the random intercepts and potentially also the random slopes. Random intercepts account for variability in the dependent measure on average. Okay, so a by-participant random intercept models the differences in the mean dV across participants. So we will have a grand average, which could be our intercept, for example, assuming all predictors are centered or sum-coded. And then we will also estimate the baseline dV, for example, the baseline reading time for each particular participant, in the sense that we'll estimate a random adjustment to the baseline for each participant. Because we might have a situation, for example, where we are running a psycholinguistic experiment which measures reading times, and there might be some people who generally read a bit slower and some who generally read a bit faster. So you would see that the average for person 1 might be consistently, like it might be higher, like the data points might be consistently higher than the data points for person 2. And to account for this by person variability of the average value of our dependent variable, we use the random intercept. So that's the minimum you could and should do when you have repeated measures data, is to include random intercepts for all the categories like participant or item which have repeated measures. Okay? And the other thing is the random slopes. So that's an adjustment for the slope of a particular predictor. Let's say you have a general overall slope beta 1, which is let's say, the effect of word frequency on reading time. And there you could have this overall slope estimate, beta 1, hat, okay? But you could also estimate to what extent the size, like the size of this effect of word frequency, differs depending on which participant you're looking at, by participant random slope, or which item you're looking at, by item random slope. So you might imagine that there is like this positive effect of some particular beta 1 value, let's say 2, for like the overall data. But you also have these adjustments now, which are estimated in the mixed model, where you can account for the fact that maybe some people are less sensitive to word frequency and so show a smaller effect of word frequency, even though they might still show one in the same direction as the general trend. And maybe for some people, the word frequency effect is much more salient. So to summarize sort of these two ideas, the random intercept and the random slope, imagine that you have like a small plot here, and what I'm drawing here is like the overall intercept estimate, beta 0 hat, okay, which would oftentimes, if you have centered predictors, just represent the average value. And what the mixed model can do in addition to that is it can compute or estimate the adjustments to that intercept that are needed to account for the data for particular subgroups of data points. For example, subgroup data points belonging to participant 1 or participant 2 or item 1 or item 2. So it could sort of account for the fact that, yeah, well, even though that's like the overall average, we also have by participant like this average varying somewhat, and we can estimate to what extent it varies. Maybe for some people it will be very far away from that mean, but for others it will be very close to the overall mean of the dV, which is represented here as the intercept. And what about random slopes? Well, by analogy, if you have a linear model, you would always estimate your overall slope of some predictor, which I can call beta 1 or like beta 1 hat if I'm talking about the estimator, the estimate in particular. And let's represent this as this line, which, as depending on how steep it is, it represents a different slope. Okay, and this could be like a positive value, it could be a negative value if the trend is like positive or negative. And here you could also say, okay, I have this general trend, like for example the effect of word frequency, but I also have these individual adjustments which will make the slope either like larger or smaller depending on the participant. Okay, so the overall trend is still this line, but I can see that some participants show like barely any effect, or like even an effect of the opposite sign, but most of them show something that's similar to this overall trend line here. Okay, so that's the idea. And estimating these adjustments to the slope, like this is the overall slope, but you can adjust it, tilt it to some extent, either to make it more steep or less steep. This is what the random slopes are basically accounting for. So a way to sort of visualize what is happening. Okay. And there is also a correlation parameter, which you can or cannot include in the model, depending on what you want to do. And this correlation parameter is accounting for correlations between the random intercepts and the random slopes, let's say, in the case of a mixed model with one predictor. And what does that mean, correlation between random intercepts and random slopes? Well, this would refer to a situation where you have reading times as a dV, let's say, and then you have your random adjustments for intercepts and slope by participant, could also be by item. And if there was a general trend in the data that people who have larger reading times on average also display a stronger effect of word frequency, in that case there would be a correlation between the random intercepts and the random slopes, because you would see like a larger random intercept being associated with a larger random slope. Okay, so that's the idea that if there is this relation that, the larger the average reading time, or whatever the dv is, the larger or the smaller, could also be a negative correlation, of course, the effect magnitude of some predictor. When that's the case, then we speak of a correlation. And this is something that you can include in the model to account for in how it sort of imagines these adjustments to be generated. Because the general assumption is that these adjustments to the overall intercept or the overall slope are drawn from a normal distribution each, okay? But once you include the correlation term as well, you're basically assuming that the random intercept and slope for particular participant 1, okay, that those are drawn simultaneously from a multivariate normal distribution. And as you might remember from some earlier lecture, a multivariate normal distribution, its variance is defined by a variance covariance matrix, which includes this value called rho, like Greek letter rho, which is precisely quantifying the correlation between those two. Okay, so here we have this additional parameter potentially, if we want to include it. That's sort of a choice that we can do when we specify a mixed effect model. This rho, or well, the estimate for rho, which is about the potential correlation between random intercepts and random slopes. If we don't include it, we basically force the model to assume that there is no correlation at all, that the correlation is 0. The mathematical formulation of a linear mixed model could look like this. In this case, we have a linear model with one predictor, so x1, okay, and we include, in addition to the basic terms we would have in standard linear regression, this bi-participant or bi-subject adjustment to the intercept, u0i, okay, in addition to beta 0, and I stands for a particular participant. And we also include the bi-participant adjustment to the slope, which is u1i, where I, again, is sort of the index for a particular participant. And here, in this example, we don't have by item random effects, but we could add them as well. But this is like a simple example, so we just have by subject random intercept as well as slope. And so you can see how this works, namely that we have this beta 0, which is sort of the overall intercept for the entire population of people, okay? And for each individual person, you will like add this adjustment, which could be positive or it could be negative, which sort of accounts for their specific baseline average value for the dv, which is y, which might or might not be somewhat deviating from this overall estimate beta 0. And likewise, you have beta 1 multiplied with the predictor x, but in fact not only beta 1, but beta 1 plus the adjustment to the slope, so the random slope, which is denoted here as u1i. So the 1 is for the slope, like beta 1, and 0 is for the intercept, like beta 0, right? And this I index here is again telling us that, for each individual person 1, person 2, person 3, or like any person I, you will have this adjustment which could be positive or it could be negative, and it will affect how steep the slope is estimated to be for a particular person and how much that steepness deviates from this overall steepness which is estimated by beta 1. And of course, you have residual error epsilon, okay? And what is assumed here about these by subject adjustments to the intercept or to the slope is that they come from a normal distribution, as I mentioned before. So these u0 values, or like u0i for a particular person, okay, so u0 is sort of this random variable which is generated, like whose values are generated from a normal distribution centered at 0 with a particular standard deviation, which we can call sigma u0. Okay? And so this standard deviation of the bi-subject adjustments to the intercept is also a parameter in this model. So this linear mixed model will try to estimate how large this variation in the bi-subject adjustments to the intercept is. And likewise, we also have the between subjects variability in the slope. So like how much these slope adjustments, these random slope adjustments vary. And those are also assumed to come from a normal distribution, again centered at 0, but with a different standard deviation, of course, or potentially different than the one where the random intercepts come from. So this standard deviation would be sigma u1, that's how we could call it, and this is also a model parameter. It is a value that fitting a linear mixed model will try to estimate. And then we have the residual variability, like whatever is sort of remaining unexplained variance within a particular group of data points, like within the data points that belong to participant 1. Well, that variability is our usual epsilon, and that's assumed to come from a normal distribution as well, with mean 0 and centered at the standard deviation sigma, which is the standard deviation we also try to estimate for the residuals in standard linear regression. Okay, so that's what's left and is unexplained basically by the model, the residual variance, and how much that is also estimated. And note that as specified here, we would assume that there is no correlation between the random intercepts and random slopes, because here, as it is written, we assume that each of them comes from a separate normal distribution, which are like completely independent of each other. But as I said, we will also see that we can estimate a correlation between those two by assuming that they come jointly from a multivariate normal distribution, which also includes this correlation term rho. Now, the general idea is that in the standard linear regression model, we only had one variance component. We only had sigma. But now we are basically dividing the variance into 3 variance components, namely into the within subjects variance, which is still our sigma, but we also have 2 separate variance components to account for the between subjects variability, namely the between subjects variability regarding the intercepts, estimated by sigma u0, and the between subjects variability regarding the slopes, estimated by sigma u1. So this sort of partition of the variance into within versus between subjects variance, and then for the between subject variance also differentiate the variance for the intercept and for the slope adjustments. That's the core idea or the core ability that a mixed model has compared to the standard linear regression model. The example we just saw spelled out was a mixed model which just included by participant, aka by subject, random effects. Now here we see how this model could be extended to also include by item random effects, in this case both by item random intercepts and by item random slopes. So the full specification would now look like this. You'd have your outcome variable y, and this is beta 0, the overall intercept, but now there is both an adjustment of the intercept by subject, which is indexed by I, and by item, which is indexed by j. And then you add to that, well, your slope multiplied with the predictor variable's value, but now you have both an adjustment of that slope by participant, which is indexed by I, and an adjustment to the slope for items, which is indexed by j. And the result of that entire equation, plus of course the residual error, the unexplained within group variance, that will give you the value of your dependent variable y. Okay, so much for the theory. Let's now have a look at how we can implement linear mixed models in R and what kind of syntax we have to use in order to achieve that. So to do this, let's work with the results of a picture-word interference experiment where participants had to name pictures in two conditions. In one condition with a superimposed written distractor, and in the other condition with just a line of X's on the screen. And here it was the case that all participants had to name all pictures in both conditions. And you might have a research hypothesis in mind, like that naming a picture with a superimposed distractor would take longer than in the other condition where there's just a line of X's. Usually we would realize this as a two-sided hypothesis test, even if our intuitive hypothesis is actually one-sided, like we have an expectation about the time being longer for condition A or condition 1, but usually we would do a two-sided test, which is a bit more conservative just to be on the safe side, okay? So the corresponding null hypothesis, under the assumption that we're doing, this two-sided test where we can detect either a difference of that with a positive sign, where like 1 is greater than 2, or a difference with the other sign, would be that naming a picture with a superimposed distractor does not differ from naming a picture without a distractor, right? That's what the null hypothesis would say. There is no difference, okay? And what we want to find or potentially get to by rejecting the null hypothesis would be the alternative hypothesis that there is in fact a difference. Ideally in the direction that we intuitively expect, which is that naming a picture with a superimposed distractor takes longer. Okay, so this dataset is in this data file called pwi-genint.csv, which you can also download in the Moodle from the same place where the lecture notes are. And after loading the data, making sure they are stored as a data frame, we are excluding some participants here on a somewhat arbitrary basis just to have a smaller number of participants, which makes the model fit a bit faster. That's of course not what you should do in a real analysis. In the real analysis, you want to fit your linear mixed model on the entire data set. But here, for our purposes, for these lecture notes to compile quickly and to show some examples of when models fail to converge, we are just going to fit the model that we're going to fit on a subset of the data, namely in such a way that we're excluding 34 participants, because there is this this column participant ID, which is basically a number assigned to each participant, so participant 1, 2, 3, 4, 5, 6, 7, and so on. And we're excluding all those 34 participants whose participant ID is less than 34 or equal to 34. So we will only start including participant 37, 36, and so on, which here in this case will, as we will see, results in a data set where we have just 19 participants left, but 34 have been excluded, okay? And we will convert the column containing the participant IDs to a factor, and we'll do the same for the column target, which is sort of our item column here. So there are different items in this experimental design, and they're called targets, so we also want to have that as a factor. That will be another random factor for us, actually. We also have condition, which is the column that specifies what condition I'm in of the two that I mentioned, so the one with a distractor versus the one just with axis, without the superimposed distractor. We want to have that as a factor too. And we want to specify contrast coding as sum coding, so that's what we're doing using this vector minus 0.5 and 0.5. These are balanced data, so this will result in the sum contrast for the two conditions. What we're also doing here additionally is to define a new column, contrast condition, where instead of having this factor data type, we just have a numerical data type. So this will literally now just include values of minus 0.5 and 0.5 directly. Namely, when the condition is baseline, it will have the value minus 0.5, and when it's the other condition, it will have the value 0.5. Okay, so after doing these small modifications to the data set, we can have a look at the summary so far. So if we print out the summary of this data frame using the str command, we see the content. So we have 3,200 observations roughly of 8 variables. The first one is the participant ID, which now has 19 different levels, so there are 19 different participants. Recall that we've excluded a bunch of them just arbitrarily for this demonstration of the analysis. That's not something, again, that's sort of reasonable to do, but here, just for our purposes, we are treating the data as if we just had sort of collected data from these 19 participants without including the first 34. We have the target, which is sort of the item. So there are different words which are the item. So it appears to have been an experiment on German. So we have Adler, Ananas, and so on. We have other information like the trial position, like at which point in the experiment the particular observation was, like right in the beginning or later. Some other stuff, we have the condition, which is, the factor with our two levels now, the baseline versus this phono R, which is like the other one where we had this distractor present. We have the RT, the reading time in milliseconds, as you can see, ranges from like 700-ish values up to like 900, even in one case 1284 in these first couple of entries. And we have another variable here, not so relevant for our purpose, span mean. And importantly, we have this column called contrast condition, which we've created, which is basically another way of more directly specifying this contrast coding. So but now we're actually treating this as a numerical variable. So this explicitly has now entries of 0.5 and minus 0.5, where the factor version of the same information still has sort of these labels of the levels. Here we do it directly by converting it to a numerical variable with the two values, either plus or minus 1/2, as specified by the sum contrast coding. Now, what we can do here is we can first fit a mixed model only with random intercepts for both, both by participant and by target, by item, we can say. And the way to do this would be to use the Elmer function from the LME4 package. Okay, that's the R package for running linear mixed effect models, and by extension also generalized mixed effect models. And we will call this function Elmer, which is also requiring as its first argument a formula, a model formula, kind of like we have for the standard linear regression model. And I'm sure you've seen this syntax before. So we have the dependent variable, then the tilde sign, and then we first specify the fixed effects. In our case, we have a fixed effect intercept. We can write it explicitly or not write it, but here we write it explicitly as 1 plus now our fixed effect predictor, contrast condition. And then we specify a random effect. And the way we do this is that we write it as follows. So in brackets, we will have this notation where within the brackets we have this vertical bar or pipe symbol. To the left of the pipe symbol we write what we want to have, just an intercept, which is represented as a 1, or potentially also random slopes. Then we would have to write the name of the corresponding predictor again. And then to the right of the pipe symbol we have the name of the random factor in question. So in this case, participant ID, because we want to estimate by participant intercepts. And then if we also have another random factor, in this case target, we will do the same thing, and we will again write 1 pipe symbol target, meaning we want to have by target intercepts, random intercepts, and this whole thing in brackets. And then we specify which data frame should be considered, where our data are stored basically. And once we've done that, we can run this. This will fit the model and save it, in this case, into a variable m1. And using the function fixEF, we can extract the estimated fixed effects beta 0 and beta 1 from this particular model. So what we get as a result is an intercept estimate of 844 and a slope estimate for this condition difference of 108.5. Next, using the var core command applied onto our fitted model object, we can get an overview of the estimated standard deviations of, well, either the by target random intercepts or the by participant random intercepts or the overall residual estimated sigma. Okay, so these three variance components that I talked about earlier, we can here see what the respective estimated standard deviations for each of them are. Alright, so this was a simple mixed effects model including random intercepts by participant and by item, but no random slopes. Now let's see how we can fit a somewhat more complex mixed effects model, which will include random slopes as well. But here, in this case, importantly, not the correlation parameter between intercepts and slopes. So it will assume that intercepts and random slopes are not correlated with each other. And so this model would be specified as you can see here. So we would say Elmer and then RT tilde, then again our fixed effects, an fixed effect intercept and a fixed effect slope, beta 1, beta 0, beta 1. And here now come the specifications of the random effects. And what you can see here is two changes. So before we just had a 1 next to the pipe symbol, and we only had one pipe symbol. Here we have two pipe symbols. This is telling this call of the Elmer function that we do not want to estimate correlations between the random intercepts and the random slopes. Okay, so we are basically making the hard assumption that the random intercepts and the random slopes come from two separate normal distributions and there is no correlation between them. Like they're not assumed to be from this multivariate distribution where the correlation can freely vary. And that's what the two pipes do. If we just had one pipe here, it would mean that we also have the correlation parameter. We don't constrain it to 0. In that case, the model would be even more complex. So two pipes mean less complexity, but sort of harder assumptions. Okay, so that's what's happening here, and we're doing the same thing both for participants and for targets. And as you can see here, we also now have not just one, but plus contrast condition. So we now tell the model we also want to estimate random slopes, not just random intercepts. The rest is all the same. We feed this function called the data frame df in our case, and after fitting the model, we can extract the estimated fixed effects beta 0 and beta 1 hat by calling fixf on that model object. And here we can see very similar result as before. So 844.5 roughly was the intercept, and the contrast condition slope estimate is 108.6. Okay, not entirely the same numbers as before, but pretty much the same. Okay, so very close to the values we got from the earlier model. And now the interesting thing is that if we now call variant var core, like this function on this model object, we will now see that we have additional variance components now, namely the variance component which is about the standard deviation of the random slopes by target, and the one that's about the standard deviation for the random slopes by participant. So this one and this one, because these are the two new random terms we've added compared to the model that we had earlier. So here we have 1, 2, 3, 4, 5 different variance components overall, right? Okay, now the next step, like adding more complexity, would be the model which includes all random intercepts and slopes and also the correlation parameters. Like it assumes that the intercept and slope by participant or the intercept and slope by target, like they could be, like the intercept and slope could be correlated with each other in the way that I explained earlier, so that maybe people who have a higher average of the DV will also display a larger or a smaller effect. Like there might be a tendency like that, which can be modeled by assuming that they come from this multivariate distribution with this correlation, with this covariance also factored in. And that's what's happening here. So here, this looks all the same as what we just saw, only that now we have one pipe symbol as opposed to two. And this one pipe symbol is basically telling R that we want to also estimate this correlation. Okay, so we fit this model, and you can see a warning here. This is a warning that indicates that the fitting didn't work entirely as it should, which is often the case with models that are too complex for the data. So this is already sort of a warning that maybe your model structure is too complex and you should reduce it because it couldn't estimate all the required parameters reliably. So when we call fix f on that model, we now see again our intercept and slope estimates, the overall estimates that is, the fixed effect ones. And when we call var core here, now you can see one new thing. So we have the estimates for the standard deviation for well, the random intercept by target and the random slope by target, as we saw before, this one and this one. We also have the standard deviation of the random intercepts by participant and the random slopes by participant and the residual error, but we also have this estimate for the correlation parameter. So we have an estimate for the correlation between by target intercepts and slopes, and we also have an estimate for the correlation between by participant intercepts and slopes. Now note one odd thing, which is that the correlation estimate for by target intercepts and slopes is 1. So this would indicate a perfect correlation, which is surely not what we would expect and what the data should show. This is in fact an artifact of a singular fit, like of this convergence that didn't really, of the model that didn't really converge well, like it couldn't find stable and sensible parameter values for all of the parameters. And what you often see is that then the standard deviations or like the correlation parameters for the random effects have these weird values, like being exactly 1 or exactly 0. So this should be kind of a red flag to that should make you consider to simplify the model structure here and not keep all of the parameters, including the correlation parameters, because you get this warning, and you also see that this correlation is unrealistically estimated to be a perfect correlation, which is surely not the case. So this is like to be taken with a grain of salt, because this is not really a sensible estimate for the correlation parameter here, but it's the best the model can do, and it also gives you this warning telling you that probably it's not entirely trustworthy as regards all of the parameter values for the random effects. So now the big question is, of course, which random effects should we include? Like we saw 3 different models, one only with random intercepts, one with random intercept and slopes but no correlations, and finally the model that had all of it, the random intercepts and the slopes, and also the correlation parameters between those two. So how can we decide which one to pick, and what strategies can we use to do that systematically? So at least in principle, we should aim to include all random terms supported by the design, by the experimental design. This is what we call the maximal random effect structure. We will see in a moment how we can identify the maximal random effect structure supported by the design. Just a short note that we have this general aim, which is to include everything that's sensible to include. But then there's like the reality of our model oftentimes being too complex to be supported by the data. And in that case, we'll get all sorts of convergence warnings about singular fit or other ones. And in those cases, we have to simplify the random effect structure, not because the random effects don't make sense conceptually, but because practically our model can't converge well on a data set of the kind that we have. So there's these sort of 2 competing aims. We want to have the maximal random effect structure supported by the design, ideally, but oftentimes, especially with frequentist statistics, with the kinds of models that we are fitting here with the Elmer function from the LME4 package, we often fail to fit a model that's very complex, even though it would be justified by the design. And in that case, we will simplify the model structure, in particular the random effect structure, out of that necessity to find a model structure which converges well on the data set at hand, okay? But let's talk about this aim, this theoretically ideal aim first, which is to include all random effects supported by the design, and let's ask ourselves, how can we identify them? So what does that mean, random effects supported by the design? Well, we should first determine what the random factors are in our experiment, in our given experimental design. And a random factor is always this sort of categorical variable that we're not interested in as a predictor, but we just have to account for it, okay? So something like a participant or item in psycholinguistics, right? So you have this categorical variable whose levels are the different participants, participant 1, participant 2, participant 3, but you're not really interested in predicting that there is some meaningful effect of participant on your outcome. Instead, you're really just wanting to treat this as a random factor. You want to account for the fact that there is this grouping within your data, that multiple data points belong to one participant and then multiple data points to another one. So you have these subgroups which make the overall set of data points being not identically and independently distributed. But we want to account for that, and that's why we want to include them as a random effect. In psycholinguistics, as I said, that could be something like participant or item typically. But you can also imagine how this concept extends to like other fields of research, like in educational research. You might have something like school, like you measure things about different schools, about pupils, like students from different schools, and you want to include school, that category, like which school you're looking at, as a random effect, if there are multiple observations per school. Likewise, teacher could be a random effect, or pupil, like the student. Or in biology, you could have something like fish, like the particular fish you're looking at in a sample of fishes, and you did like multiple measurements on one fish. Or river, okay? You did measurements on multiple rivers, and for each river you have more than one observation. In that case, you should include river as a random effect, unless you're like interested really in predicting some between river differences as a predictor. Then you should have it as a fixed effect, as a categorical predictor. But if that's not the case, then have it as a random effect, just as participant or item in psychology and linguistics. And as I said earlier, that also allows you then to draw conclusions about the population of the category in question. So the population of participants might be the population of German native speakers, from which we have taken like a sample of, 50 people to run an experiment. And by including participant as a random effect, we're also making sure in a way that our statistical inferences can be generalized to the population, to the assumed population out of which my sample of participants came, okay? So that's what we should do, like identify what random factors exist in our design. And one conceptual distinction that is worth addressing is the relation that different random factors can have to each other. Is it nested or is it crossed? What is the difference? So two random factors are considered to be nested when one of them is made of a subset of the other. Now, what do we mean by that? So let's take the example of pupils and schools. The same would also work for fishes and rivers, for example. So if we have our random factor school, which might have multiple levels, so there might be different schools that I took some measurements of, or like to be more precise, measurements from like the pupils, like test scores or something. So this could be school, which is, so you have school A, school B, school C, D, E, and so on. And within each school, there are different pupils, different students, right? So you have student 1 in there, student 2, student 3. Let's say there are 3 students in that school. Obviously, in real life, there should be more than 3 students per school, but this is just our toy example. And now the crucial idea is that if I look at the students in the school B, I will see a different set of students in school B. So there will be student 4, student 5, student 6. and so on, student 7, student 8, student 9, student 10, 11, 12, 13, 14, 15. So the thing that you should realize here is that, of course, right, of course, the same pupil will not be in multiple schools. So the random factor of student is nested within school. It's not crossed. Crossed would mean that you would have the student 1 appear in all the different schools. But you have student 1 only appearing in one school. That's why the relationship between school and student is a nested relationship between these two random factors. But take the example of a psycholinguistic experiment. There we have a different situation, because if we have a psycholinguistic experiment, our two random factors look as follows. So there I have multiple participants, right? And I can label the participants A, B, C, and D, and so on. So I can have participant here, and here another one, and third one, fourth one, fifth one, and so on. And so these will be my participants, A, B, C, D, and E. And now comes the crucial difference, because now within each participant, I always have the same items. So I will have item 1, item 2, item 3, but also item 1, item 2, item 3 for participant B, item 1, item 2, item 3 for participant C, item 1, item 2, item 3, right? So it's always the same items that are presented to each participant. In other words, these two random factors are crossed, because item is not nested within participant, because the same item appears across all participants. That's why we have this crossed relationship between these two random factors. So participant item, usually at least in the common kinds of experimental designs you see in psycholinguistic, will always be crossed random factors. That's the default case that you most often see with the kinds of data that we are working with here. And this is, of course, as you see here, a property of the data, not necessarily something about the model. Obviously, the model should be specified in such a way that it reflects the structure of the data, okay? But it's not something that you can decide on in how you construct the model once you already have fixed what the data design and structure is. So it's really something about the data, and in the model specification we have to make sure that we account for it accordingly, okay? All right. The next step would be to decide which random intercepts to include, and here the decision is fairly simple. All random factors can and should have a corresponding random intercept. So all of the random factors we've identified should be accounted for at least with random intercepts. And the next and a bit more tricky question to answer is which random slopes should I include? Now, among the random factors we've identified, we have to ask ourselves, are there experimental manipulations, variables, like basically predictor variables, that vary within these factors? Or like, in other words, do those manipulations vary within or only between the random factors? Let me give you an example of what that would mean concretely. So let's take the age of a participant. Let's say that was a predictor that we had. Now, age cannot, by definition, vary within participant, right? There is only one age value for one participant. There are not multiple age values unless you do like a longitudinal study or something like that. But in a simple psycholinguistic experiment where people come to the session once, they have the same age in the entire data set. Their age doesn't vary, okay? It's always one participant, one age. So that tells us that the age cannot vary within participant. Therefore, a random slope for age by participant would be nonsensical. Like, it would be a bad thing to do because there's nothing to estimate there. The effect of age does not vary by participant because it's undefined for a single participant, because one participant just has one age, one data point for age. It can vary within items though. So within one item, you can have, and you will have, multiple data points coming from different participants with different ages. And it might be that there is some overall effect of age on reading times, but that it is more pronounced or less pronounced on particular items in your experiment. So that's in principle possible. It doesn't mean that it should happen or that you should necessarily expect there to be a strong modulation of the overall effect of age by item, but it could be something that could be in the data, just deducing it from the structure, because age can in principle vary by item, within item, I mean, okay? That's why a random slope by item for age would be a very sensible thing to include. It would be part of the maximal random effect structure justified by the design. Another example, if we have a variable like frequency, frequency of a word, this of course cannot vary for a given word, because one word has a fixed frequency as defined by measuring it in some corpus data. So if word was a random factor we had, then it would not make sense at all to include frequency, random slopes for frequency by word. What we can do though is we can include random slopes for frequency by participant, because for one participant we can have multiple observations of words they read, and it might be that there's an overall effect of frequency in the data set, but for some people, if you look just at their subset of data points they produced, this effect of frequency was more pronounced or less pronounced than for other people, right? So frequency word frequency can vary within participant, because you can have multiple data points within a single participant regarding words that have different frequencies. So that makes sense. We can do that. We can have a random slope for that, but not a random slope by word or by item, aka by item if item really means word here. Now, sometimes it's the case that whether a predictor varies within participants or items also depends on the exact experimental design we're looking at. So there are different ways to set up a study, and let's say, for example, we had a study where we compare the processing of concrete and abstract words. Now, in principle, we can have this as a within subjects design, within participants design, which means that all participants see words from both conditions, both from the concrete condition and from the abstract condition. So in that case, yes, the concreteness of words does vary within participant, therefore it would make sense to have a random slope for concreteness by participant. But if our design is set up differently, that is, if our design is a so-called between subjects design, meaning that we are recruiting one group of people that will only see the concrete words and an entirely separate group of people that will only see the abstract words, in that case, in the specific experimental design we now have, it would not make sense to include a random slope by participant for concreteness, because in this design, set up as a between subjects design, the concreteness would again not vary within participant, because by definition of the design, each participant would only ever see one type of concreteness, namely either the concrete words or the abstract words. So that's also something to keep in mind. You always have to think about whether or not a predictor varies with regard to some random factor like participant within the context of your specific experimental design. And that might also make a difference if it's like a between participants or a within participants design. One way to quickly find out, given a data set, whether or not the values of a predictor vary for within one level of a random factor, is to plot the data accordingly. And how to generate such a plot is what we're going to see now. So for this illustration, we're going to use a data set that we've already encountered in homework number 6, which is a data set from an experiment testing the effect of the age of acquisition of a particular word on the time that is needed to name a picture representing that word, okay? And this data is in this data file eeg underscore div underscore rt and so on, which you can also download from the Moodle, of course. And here in this experiment, all participants named all the words that were tested. We can load the data, and after doing some minor edits to it, we can have a look at the structure. So what is notable here is, of course, the latency, the naming time, basically, the amount of time people needed to name a picture. And we have the age of acquisition of a word, which can be either early or late, so it's like a two-level categorical variable. And we have PPID, which is an identifier for particular participants. Okay, so all these first couple of observations in this data set belong to subject number 101. Okay, that's how they are labeled here. Now, what we can do is, okay, we can define contrasts here for the age of acquisition predictor, but the interesting thing really is here to create this XY plot, which we could do using the XY plot command, and then do latency tilde age of acquisition, pipe symbol, and then PPID, which is the random factor we want to examine here. And as the data, we're going to specify, well, our data set, in this case it's called mydata2. And the plot that you see here basically gives you a quick overview of the data points, but grouped by this random factor PPID. And you see on the x-axis now the values of the age of acquisition predictor variable, and on the y-axis you see latency, the outcome, okay? And so what you can see here quite neatly is that, for example, for participant number S116, you can see that there are both data points for early acquisition and for late acquisition, right? So that makes sense because this AOA here is a property tied to particular words. So there is certain words that are considered to be acquired early in life and certain words considered to be acquired late in life, for example, more technical terms and so on. And so this experiment is really about all participants seeing all the words. Therefore, all participants will have encountered both early acquisition words and late acquisition words. And you can see that, you know, there is no exception. Like literally all of the participants have data points for both levels of the predictor. So what does that tell us? Well, it could tell us that it would make sense to have random slopes by participant for age of acquisition, right? Because there might be some general effect of age of acquisition we want to estimate, like maybe that lately acquired words take longer to be named in general, but that this effect can differ between participants, and that we also want to estimate these adjustments to the slope of that effect, which we can do if we have, in fact, data points from both conditions within a single participant, which is the case here. We can clearly see that. So that's a visual check to answer that exact question, like can we include a random slope here based on the design? Okay, here we can and should. Now another thing we could do is to create the same kind of plot, but now instead of creating it for PPID, we could create it for item. So an item here is literally a particular word, right? So the item could be, it's a study in French, so pingouin, volant, souris, and cube, okay, so different French words. And here we see that for, like within a single item, okay, it's kind of awkward, the font is too big, but you can still sort of see that there should be like the word, how it's spelled in each of these subplot titles here. For example, the word sac, okay. This only has data points for the late condition of the age of acquisition predictor, which makes sense because we just established that age of acquisition here is a property tied to words. So a word can either be early or late acquired. It can't be both. Therefore, there can only ever be data points within a single word belonging to either the late or the early condition, but not to both. So here, for participants, this was possible. We had data points for both conditions within a single level of a random factor, within a single participant. But when the random factor is item, here in this design, that's not sensible anymore. We only have either early data points or late data points, but we don't have both within a single of these like small squares which represent a single level of the random factor. Therefore, here it would be not possible, not sensible to include random slopes by item for age of acquisition, because there is no item, like word-specific slope to estimate it all, because there are no two levels of the predictor to compare within a single word, right? There is, within a single word, only ever data points from one of the two levels, either from late or from early. Therefore, in summary, we should only include by item random intercepts here, but no by item random slopes. Our next topic here is how and when to reduce the random effect structure. So by now we've established, hopefully clearly to you, how to identify the maximal random effect structure that's justified by the design. But I've also alluded to the fact that we can't always hope for that maximal random effect structure to actually produce a model that can converge on our data, because our data might just be too small for such a complex model to be fitted to. And in that case, we have to face some practical considerations of basically deciding what's the least damage I can do by simplifying the random effect structure without violating too many assumptions about my data. So we should always try and aim to fit the maximal model that's justified, but sometimes we have to make a compromise and simplify it in order to get the model to converge. So there are two kinds of consequences that you might face when the model is too complex. Either the models do not converge at all, that will be highlighted by very explicit warnings, or the models do converge, but values for some random terms cannot be trusted because they are, exactly 1 or exactly 0, which is usually a sort of sign of non-optimal fit, let's say. And there we have to decide wisely how we can simplify the structure. There are different views on how to proceed there, like which model parameters to prioritize and which to throw away. You can have a look at these two references, Barr et al. 2013 or Matuszek et al. 2017 for like two perspectives. In general, unfortunately, there's like no one size fits all cookbook for that, but we have to sort of come up with a way that works for us. Okay, so I've mentioned this idea of convergence warnings. So R will typically warn you or throw out an error when the model doesn't converge. It will indicate that even though you might be able to print out a summary of the model, the estimates of the parameters will not be trustworthy if there is a convergence warning, right? So it means that something went wrong, and even though it ended up on some parameter values, these will be sort of corrupted in a way. So you shouldn't trust a model that didn't converge properly. If you want to read more on that, you can have a look at this blog post here, but that's again a bit beyond the scope of our lecture. So one thing you should do to maybe certain that convergence is okay or isn't okay is to look at the actual values of the random effects parameters, like the random effect standard deviation and also the correlation between intercepts and slopes. And typically, if you see like a correlation that's 1 or close to 1 or a standard deviation of 0 or close to 0, this would suggest that the model had trouble estimating that particular term. Another thing you can do is to use likelihood ratio tests to compare two models of different complexity, where one of them is reduced by one particular parameter. For example, a model with the correlations versus a model without the correlation parameters, or a model with a certain random slope versus a model without it, and use a likelihood ratio test to identify whether including or removing that additional parameter accounts for a significant increase or loss in the amount of variance explained. Okay, that can also help you decide on whether you should or shouldn't throw out a parameter when you try to simplify the model structure. Let's see an example of that. So we had our model 3 from before, which was the model on this earlier data set of reading times, where we had these two conditions, and we had participants and items, or targets as they were called here, and we had this maximal random effect structure including all random intercepts and slopes, and also the correlation parameters indicated by the fact that we only have a single pipe symbol for both subjects and participants. And now, as you remember, this was our variance output here, so we could see that there is this fishy kind of correlation of 1 for the by-item random intercepts and slopes. So that might prompt us to refit this model, but without this correlation parameter that apparently had like a hard time of being properly estimated. So how to remove this correlation parameter for the targets? Well, we can add this double pipe symbol for the specification of the random effects by target. We'll still keep the correlation estimation for the by participant random effects because that seemed fine, okay? And we can refit our model and call it M3B maybe. And what we could do now is to, as suggested here, run a likelihood ratio test comparing these two models. So the one including this correlation and one excluding it. And what we see here is that the outcome of this likelihood ratio test is in fact actually significant. So it would mean that even though this correlation is kind of weird and it didn't seem so important, it does in fact account for a significant amount of additional variance. So based on that, we could decide to actually keep this parameter in, even though at first glance it looked sort of nonsensical with this correlation being equal to 1. So that also shows us that convergence warnings can often be, but are not always problematic, and they signal us to double check, like in this case where we might like fit a comparable model but without a parameter that looks weird, for example this correlation that's equal or almost equal to 1, and see if when we compare the two models if it still accounts for additional variance, and if it doesn't, or if it's not significantly accounting for more variance, then we could decide to throw that parameter out for good, okay? So that's sort of like a kind of vague and exploratory heavy area of this entire linear mixed modeling framework, because it will often depend on like your particular data and situation at hand on how to best proceed to simplify the random effect structure. As I said, there's like unfortunately no one size fits all best way to do it. Therefore, this will also not be something that you guys will be asked like to decide on how to reduce the random effect structure, particularly because there are so many different ideas and opinions on how to best proceed on that. But what might happen in the exam is that you should identify and choose the maximal random effect structure supported by the design, and to make sense of the random part of the model output, like try to understand and be able to say in your own words what the standard deviation for the random intercepts or the standard deviation for the random slopes by participant, for example, means. Okay, so that's something that you should be able to do, but you won't be asked to do the reduction of the random effect structure because that's just a too vague and ill-specified thing anyway, so that's not something that you will be asked. But please try to understand conceptually what the maximal random effect structure justified by the design is, and also try to be familiar with how to interpret the summary, the model summary output from Elmer regarding the random effects, okay? So let's look at that for a little moment, like how to interpret the random part of the model output. Well, the random part of the model output answers these questions. So first, do participants vary in the average of the DV, for example, response times, and if yes, by how much? That is quantified by the standard deviation for the by participant intercept. Then there is the question, are all participants impacted similarly by the experimental variable, by the experimental manipulation, our predictor? If not, how much variation is there? This is estimated by the standard deviation for the biparticipant random slopes for our experimental variable. And there's also the question, do participants with slower responses show more or less of an effect? Now, this is a question that's answered by the estimate for the correlation between intercepts and slopes, because that's precisely the relationship asked for here, right? So slower responses overall means higher intercept. And so we're asking if higher intercepts tend to be associated with larger or weaker effect sizes, or if these two things are completely independent of each other. If slower responses are associated with larger effect sizes, we should see a positive correlation. The extremest possible would be 1. If they are completely independent, the correlation estimate should be close to 0. And if there was a negative correlation, that is that slower responses are associated with smaller effect sizes, then we should see a negative correlation. The most extreme possible would be -1. And this is all about participants. The same kinds of questions can also be asked about items, of course, regarding the random effects by item. Now let's have a look at this in the actual model output from the model M3 that we fitted earlier. You can see the random part of the model output here. It has this title, random effects, right? And as we saw earlier, we have the standard deviations that we just talked about, which quantify the amount of variance in these, the amount of variation in these adjustments for the slope and the intercept for item and for participant. And we also see the correlation parameters as we saw earlier, right? So these would be regarding this third question here. We can also extract just this random part of the output, as we saw earlier, using the var core function, and this will now just provide us the information about the by participant or by target standard deviations for random intercepts and random slopes, and the correlation parameter and the residual variance, all just in one compact output without all the other components of the model summary. So that's what we can do if we just want to have a quick glance at only the relevant output for the random effects. Now, the random effect summaries we've seen so far were just providing us information about the estimated amount of variation represented as a standard deviation, for example, in the random intercepts or slopes, and also the estimated correlation between them. But what if we want to have a look at the specific participant by participant or item by item estimates of the intercept or slope adjustments? We can do that by using the function ranef, like ranef, okay? And we can apply it to the model that we care about, the fitted model object. If we do that, in this case, let's say for M1, which was the first version of the model that we fitted earlier, just including random intercepts but no random slopes, we will see the following output. So we will see the output which tells us for each word, for each target, each item basically, what the estimated intercept adjustment is. So we had this overall intercept, remember, which was 845 roughly, I believe, right? And here we have numbers which can be positive or negative, which represent the adjustment for each particular item. So for Adler, for Ananas, for Antenne, you can see how much the intercept for that particular level of the random factor is estimated to deviate from the overall intercept, okay? So if you recall the mathematical formulation of the model, this would be like, so beta 0 would be the overall intercept, and then UO1 would be this, UO2 would be this, UO3 would be this, UO4 would be this. So, you know, these are like the item-specific adjustments to the intercept. So you can see that Antenne, for example, has a somewhat higher average naming or reaction time, while, let's say, banana has a somewhat smaller than average mean reaction or naming time. Okay, so that's how to read these estimates, and we get an estimate for each of the items that we have, just as we get an estimate if we do the same thing for or we look at the output for participant, which is the other random factor. We see the 19 participants included here. As I said earlier, we removed the first 34 participants here just to keep the model a bit simple, the data a bit simple, just for demonstration purposes. So here we have participants 35, 36, 37 up until participant number 54. And here you can see their respective random intercept adjustments as they were estimated by that model M1, which just had the random intercept. So participant number 35, for example, was a bit faster than average, like he had an average reading time, or what was it, reaction time that was smaller than average, whereas, for example, participant number 36 was considerably slower than average, like they had this intercept adjustment of plus 105 estimated for their data. Okay, so that's how to read this output here. So you could then ask questions like, okay, what is the estimated response time on average for item ananas? Well, in order to compute it, you would have to take the estimated overall intercept, which was 845 roughly, and then add to it the intercept adjustment for ananas. So 845 plus minus 44, that would give you about 800 or 801. Okay, that's how you could calculate that. All right. So the last thing we can do is to visualize the estimated variability by a random factor, for example, by participant. As I mentioned earlier, these adjustments, random adjustments for intercepts or for slopes, are assumed to be distributed like a normal distribution, with mean 0 and the standard deviation being the one that's estimated from the data. Okay, so once we have our output, we can also try to plot this between participant variability in the average reading time. So here for this plot we could use as the average of, the actual estimated overall intercept, which was 845. And then we can use the standard deviation that we got from the random output of our model as this estimate for the between participant variability. So then this plot, which is basically generating a lot of values from this normal distribution with mean 845 and standard deviation as specified here, and then sort of just plots it as a density plot. This plot, shows us the shape of this normal distribution, and it gives us a glimpse of how large or small the between participant variability is. Okay, so you can assume that if you just were sampling more and more participants, then their average reaction times would follow this kind of distribution. That's what our model is basically estimating. Okay. Now, what you can also do is to display the between participant variability in effect size of h of acquisition. So this is now about the random slope for acquisition as opposed to the random intercept by participant. So here again, the idea would be to take the overall estimated effect size, like beta 1 hat, which was 108 roughly, and then have that as the center of this visualized distribution here. And as the standard deviation for this normal distribution, we will take the standard deviation for the random slopes variability that was estimated by our mixed effects model. And if we do the same kind of plotting procedure again as for the random intercept, we'll get this kind of visualization here, which shows us the probability density function for a normal distribution with mean being beta 1, or like the estimated beta 1, and the standard deviation being the estimated between participant variability in effect sizes. So this will tell you that, okay, the model estimates that if you were to sample more and more participants out of your population, then and you would measure the effect size in each of them, then the degree of variability of these effect sizes across participants is represented by this distribution here. So for some people, the effect size will be just 50 milliseconds. For some, it will be 150, or in some rare cases 200, but like barely anyone has an effect size of 0 and barely anyone has an effect size of 250, let's say. That's what this this visualization of the between participant variability can basically convey to us, okay? All right, then last and really final thing, just some thoughts about power for mixed models. So recall that we had talked about the concept of statistical power in one of the very early lectures there in regard to the t-test or to the standard linear regression model. Now the thing with mixed models is that for mixed models we can only compute power using simulation. So while it was true that, for example, for the t-test there are ways to analytically compute the power, you know, there is this power.t.test function which uses some fancy analytical math underneath to like directly compute the power for you. This kind of thing is not possible with mixed models. So for mixed models, we can only rely on power analysis through simulation. Okay, we've seen an example of power simulation before for the t-test when it wasn't really necessary. Here, it's really the only way we can tackle the problem. So what does power simulation mean, or like power analysis by simulation? Well, the idea is that we generate data under certain assumptions from a hierarchical data structure that is assumed by our linear mixed model, and then we repeat this like simulated data generation process a lot of times, and each time we will then fit our linear mixed model to these artificial data sets that are generated like in all of these potentially thousands of iterations, and we are going to then each time fit the model and see if our effect of interest comes out as significant or not. And then we're going to take the proportion of cases in which the effect came out as significant and divide it by the overall number of cases or like iterations of that power analysis. And the resulting proportion of like cases where the effect was detected as significant, as opposed to the overall number of cases, that will be our power estimate, okay? Because that literally then represents the proportion of cases where we find an effect if there really is one. And what's underlying as an assumption of all of the iterations in the simulation is that we have a fixed assumed true effect size which is not 0, okay? So the general intuitions about power still apply, also in the mixed model case. So power depends on 3 things. First, the sample size, where larger sample sizes are associated with higher statistical power. Second, the variability in the data, where more variability is associated with less statistical power. And lastly, also the true effect size that is assumed. So if the true effect size is very large, then also this will be associated with higher power, whereas if we try to detect very small effects, then the power will be less. And here in the mixed model case, this variability can be subdivided, again, as I said earlier, into different kinds of variability. So we have the residual variability, which is just the unexplained variance epsilon. But now we also have these other variance components, like the variability in the average dependent variable values across participants, which is captured by our random intercepts, or the variability in effect size across participants, which is captured by a random slope, okay? So all of these components of the random effect structure and the values of the variance components will affect the statistical power that we can have in a data structure that we want to analyze with a mixed effects model. And this is basically what we're going to look at in the next 1.5, you could say, video lectures in the next 2 weeks, and also for the remainder of this course. This will be our last topic. namely to run these simulation-based power analyses on data that we simulate for repeated measures designs, like the typical kind of hierarchical data structure designs that we have when we run psycholinguistic experiments, for example. And yeah, that's again a small teaser for the next 2 weeks. A general recommendation regarding how to achieve higher power when you already have some pilot data to look at, for example, is the following. So this is explained and recommended in this source Westphal and colleagues 2014. Say you've already conducted a pilot experiment with a particular number of participants and a particular number of items, and then you find that, let's say, the items have a very high variability as regards the by-item random intercepts and slopes that you can see in the model output, and like a much higher, like considerably higher variance than the variance by participant. In that case, it would be recommendable to increase the number of items before running the main study that you want to run. Okay, so run the main study with a higher number of items as opposed to the pilot study, but maybe you want to keep the number of participants fixed because the variance there wasn't so big. Whereas if you see the opposite, if you see that there is still a high by participant variability in random intercepts and slopes in your pilot data, but the by item variability is not so large, then the more efficient strategy to reach higher power faster would be to have a new study with more participants. Okay, so at least assuming that getting new participants and new items is sort of equally hard. Maybe in practice it's more costly to have more participants, right? But at least from the statistical point of view, you should try to increase the random factor which shows the larger variability in like an earlier preliminary data set, like a pilot data set. Okay, so that's the last point I want to make today. More on this, again, we're going to see in the next 2 weeks. Here you can see the references listed that were cited throughout this video lecture and in the lecture notes here more specifically. And yeah, that's it for today. See you guys in the next video lecture then.